7.6, the cross product of two vectors. So the cross product, this is denoted by vector A, and then it looks like a multiplication symbol, but it's actually cross symbol now. Okay, cross vector B, also called the vector product. And this is used in physical applications and in understanding of the geometry in R cubed. The result of the cross product is a vector. So it's not a scalar like the dot product. Okay, it's going to be in the form like x, y, z. Okay, by calculating the cross product of vectors A and B, we're calculating the third vector C that's perpendicular to both vectors A and B. Okay, so this is what it yields. Please note, if we are given two non-zero, non-collinear vectors, there is an infinite number of vectors that are perpendicular to each of these two vectors. And in this case, we just choose one of the vectors. So, example 1, given the vectors vector A and vector B, we're going to determine the cross product of A and B. So we're going to do this like the old school way. We're going to do this one via dot product. Okay, so we're going to have, let's go vector V is going to be x, y, z. So if we did A dot V, we're going to get 1, 1, 0 dot x, y, z. And that's going to give us x plus y equals 0. And then if we do vector B dot vector V, we're going to get 1, 3, negative 1 dot x, y, z. And we're going to get the equation x plus 3y plus z equals 0. Now, these two equations here, what we'd want to do is we would want to put them into a matrix. Remember the coefficients. So coefficient of x is 1, coefficient of y is 1, coefficient of z is 0, and then it equals 0. Okay, and then the second equation as well, coefficient of x is 1, y is 3, z is 1, and then we have 0. And then we want to apply operations to simplify. So this row 2, we're going to subtract row 1. Okay, so we're not actually touching row 1. We're not doing any operations to it. So we're just going to rewrite it. And then row 2, we're going to subtract row 1. So 1 minus 1 is 0. 3 minus 1 is 2. 1 minus 0 is 0. And 0 minus 0 is 0. Oh, sorry. 1 minus 0 is 1. 0 minus 0 is 0. Okay, so if we were to rewrite this equation here, we would still get x plus y equals 0. Now, if we rewrote this equation, we would get 2y plus 1z equals 0. Okay, rearrange these. I'm going to bring over the y and I'm going to bring over the 1z, and we're going to get, so these are going to be x equals negative y, and we're going to get 2y equals negative z. Oh, this was negative, negative, negative. Sorry, that's going to be negative, so it's going to be positive z. Okay. So, now, since all of x, y, and z can be expressed in terms of y, what we're going to get is, let's bring this up here, okay? So if we have x, y, z, the y we're going to leave alone. Now we can write x in terms of y, it's going to be negative y, and we're going to write z in terms of y, it's going to be 2y. Okay? In other words, it's going to be y times negative 1, 1, 2. So we can say all can be expressed in terms of y. Okay. In other words, let's write a conclusion. So the solution is going to be y, -1, 1, 2, or simply k, -1, 1, 2. Okay, and then k is going to be an element of the real number system. So essentially what's going to happen is any scalar multiple of this -1, 1, 2 is going to be perpendicular to both of these. Okay, so this is the approach if we use the dot product. Okay, now we're going to introduce the equation for cross product. Okay, so deriving the formula for cross product. When we cross two vectors, there are infinitely many vectors that are perpendicular to the first two vectors. Okay, all of which are scalar multiples of each other. So the cross product only exists in arc cubed, since the perpendicular vector that it constructs must be outside of the plane of the first two vectors. Okay, so here's the definition of cross product. The cross product of two vectors, say vector A and vector B, okay, and of course it only exists in arc cubed, is the vector that's perpendicular to these two vectors such that vector A and vector B and A cross B form a right-handed system. Okay, what that means is that if you hold up your right hand and you separate your index finger and your middle finger, these two are going to create two vectors. Okay, this here on this diagram is in the background. Okay, don't think that it's just like complementary angles. This is in the background. So we have vector A and vector B, and then we have some thumb, which is going to be vertical, and that's going to be perpendicular to both A and B. Okay, the vector B cross vector A is the opposite. So all that means is the points are in the opposite direction. So it's like multiplied by -1. So here is the formula. So it's going to be some scalar k. So all this means here is that we can multiply the vector by any scalar, and it's going to yield just a scalar multiple of that vector. So if we had vectors A and vectors B here and here, so it's A and B, okay, this vector could be perpendicular, or this one, which is 2 vector v, could be perpendicular, or 3 vector v can be perpendicular, right? So it doesn't matter. It has to, like vector v is going to be perpendicular regardless. Any scalar multiple of vector v will also be perpendicular, okay? That's what that means, okay? If k equals 1, then this long equation, I'm going to show you how to get this. A cross B is going to be this. And remember, these are commas right here because we're going to have 3 coordinates. It's going to be in the form of a vector. Okay, and if k is -1, essentially it's, see how it's like A2B3 minus A3B2? Well, this time it's just the opposite. A3B2 minus A2B3. Okay, and then these two would get switched and these two would get switched. Okay, so there's 2 different formulas for this. You don't have to memorize this long formula. I think it's better just to understand where we get this from. So the list method, I didn't actually know until I was working at a school in Hamilton. I learned it with the grid method, like in university, that's how we did it. But I actually like the list method better, okay? So here's the thing. You're going to have 2 vectors. Let's call them vector A is going to be A1, A2, A3. Okay, and of course commas between those. And we're going to have vector B, which is going to be B1, B2, B3. Okay, so the list method, all we do is write out vector A's components twice. A1, B1, oops, do that all the time, A2, A3, A1, A2, A3. Okay, so write them out twice, and then we have B1, B2, B3, B1, B2, B3. Okay, so we ignore the first, we ignore the last, and we deal with the middle. Okay, so the rule here is multiply down to the right, and then subtract, and then multiply up, and of course to the right as well. Okay, so what this is going to look like is, here's our equation. So multiply down, A2 times B3 minus, right, subtract, B2 times A3, B2, A3. Okay, and then we're going to have comma. And the next one, A3B1 minus B3A1. Okay, now A1B2 minus B1A2. Okay, so that is how you get the cross product. The second approach is the grid method. Okay, this I used in university. This is in component form. So we would have vectors I, J, and K to be the titles here. And then we have A1, A2, A3, B1, B2, B3. Okay, so this is the physical way that we do it. Okay, so we cover column I. Actually, I put vectors. We don't need that. It's just IJK. Oops. Cover vector column I with your finger. And then we multiply down. So I'm going to short form this. Multiply down to the right. Subtract. And then multiply up to the right. Okay, so how that's going to look is you're going to physically put your finger over this column. So you're not going to be able to see this column. So we're going to have A2B3 minus B2A3. Okay, just like how we had here. Okay, now the next one. Okay, let's do another color. Okay, now we're going to cover column J with our finger. Okay, so we're going to have J's here, and you're going to cover it with your finger. Now, this one's the backward one, so this is the only one that you have to really remember. Okay, multiply up to the right. We're going to get subtract. And then we're going to have multiply down. To the right, of course. Okay, so what is this going to look like? It's going to be B1A3 minus A1B3. Okay, and then the third one. We're going to cover the J column with our finger, or sorry, the K column with our finger. Okay, so let's write this out. Cover the K column with your finger. Okay, so we're going to multiply down. Oh, I'm going to short form this. So multiplication symbol, down, down arrow. Okay, and then we're going to go subtract, and then multiplying up. Okay, so it's going to be A1, B2 minus B1, A2. Okay, and then we're going to just take those and put them all together in component form. Okay, so either one, I think what I'm going to do is I'm going to stick with the list method. Okay, on this video, it's just easier to list this than to do the visual of like the IJK. Okay, example 2. If vector P equals -1, 3, 2, and vector Q equals 2, -5, 6, we're going to calculate the cross product of vector B cross vector Q, and then we're going to reverse that. Vector Q cross vector P. Okay, so let's do vector P cross vector Q first. Okay, so list the components of vector P, -1, 3, 2, -1, 3, 2. List the components of Q, 2, -5, 6, 2, -5, 6. The first and the last ones don't matter. So vector P cross vector Q is going to be 3 times 6 minus -5 times 2, comma, 2 times 2 minus 6 times -1, comma, -1 times -5 minus 2 times 3. Okay, so let's simplify this. So 3 times 6 is 18, minus -5 times 2 is -10, so it's going to be plus 10. 2 times 2 is 4, minus 6 times -1 is going to be positive 6. Okay, and -1 times -5 is just 5, minus 2 times 3 is 6. Okay, so we get the vector 28, 10, -1 as being perpendicular to both P and Q. Okay, now let's see if we can reverse this and get the same answer. Kind of a little bit of a proof, except for we're using actual numbers rather than the theory A1, A2, A3. Okay, so if we're going to do vector Q cross vector P, we're going to write out vector Q first, 2, -5, 6, 2, -5, 6. Then we're going to write out vector P twice, -1, 3, 2, -1, 3, 2. We don't mind the first or the last, so let's focus in the middle. Okay, so -5 times 2, and I'm going to start skipping steps actually. -5 times 2 is -10, minus 3 times 6, which is 18, comma, 6 times -1 is -6, minus 2 times 2 is 4, comma, 2 times 3 is 6, minus -1 times -5 is 5. So we get -28, comma, -10, comma, 1. So let's go ahead and compare these two. Okay, they're the same thing. They're actually scalar multiples of each other, because if we pulled out a -1 out of the perpendicular vector Q times or Q cross P, okay, we're going to get 28, 10, -1. Okay, so we can just see that these are the opposites. It's just opposite. So multiply by K equals -1. Okay, the other thing that we can do is we can check if our solution is correct. So as an example, if our solution is correct, we should do vector P dot and then vector P cross vector Q, right? Like that 28, 10, -1. And we should be able to yield a 0. We should be able to do the same thing with vector Q, right? Because vector P, vector Q, both of them should be perpendicular to the answer that the cross product yields. So if we were to do this, we'd have vector P, which is -1, 3, 2. We would do the dot product of that and our perpendicular vector, 28, 10, -1. Okay, -1 times 28 is -28. 3 times 10 is 30. 2 times -1 is -2. Okay, we get 0. We can do the same thing for vector Q, which is 2, -5, 6. We can do the dot product again with our perpendicular vector. So we're going to have 56 minus 50 minus 6, and we get 0. So we can clearly see that our answer here of vector P cross vector Q, or vice versa, is perpendicular to both P and Q. Okay. And now just a couple properties for the cross product. So let P, Q, and R be 3 vectors in R cubed, and K is an element of the real number system. Okay, so we're going to use that one for these 3 laws. So vector multiplication is not commutative. So P cross Q does not equal Q cross P. What it actually equals is the opposite of Q cross P. Okay, we just saw that in the previous method. Now, distribution law for vector multiplication. If we were to do P cross Q plus R, it holds that P cross Q plus P cross R. That holds. Okay. Now, scalar law for vector multiplication. It holds that if we had some scalar K and we multiply it by P cross Q, we could also multiply vector P or vector Q by K and then cross it by the remaining vector. Okay. We could also, yeah, so then that's KP cross Q or P cross KQ. Okay. And then, so note, usually the order of multiplication doesn't affect the product, but in the case of cross product, it definitely affects it. Okay, remember, it's the negative, it's the opposite.